Okay. With population genetics, there will be some definitions, but to be honest, they're going to be very rare. So for example, what type? What is a gene pool? What is a genetic drift? What is a founder versus a bottleneck effect? Or I can set it up for you and ask you which one is the best definition for it. What's the difference between fixed and lost? What is the source of all new alleles? What's the source of all new alleles? Mutation, right? But remember, mutation in the absence of selection is has a negligent effect, has a very minimal effect. So there has to be a selection. What is the Hardy-Weinberg law? What is an allelic versus a genotypic frequencies? But for the rest, it's going to be calculate what. So for example, if you are given, well, let's actually link this one to other. Because you will get questions 3 to 6 are all based on this given. So I can start by telling you that one gene, although I can't, yeah. Okay, let's say, well, we can still do it. Question, part 1. One gene, 4 alleles. How many genotypes? One gene, 4 alleles. How many different genotypes can you get? And they said quickly, less quickly. Right? One gene, 4 alleles. How many different genotypes do you get? 10. 4, 3, 2, 1. That's it. AA, AB, AC, AD, BB, BC, BD, CC, CD, DD. 10. Right? You can write them out if you want. So that's why I was debating, because I can't ask it in a question, because part 2 will tell you those stuff. Okay? So, but these are going to be my 10. They're going to be AA, AB, AC. In fact, let me spread them out. Or no, I don't have to. AC, AD. Right? What comes next? BB, BC, BD, CC, CD, DD. These are my 10. Okay, so let's assign numbers to these. Real quick. Making it very easy. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. I don't know if that was easy, but to calculate ultimately. But let's say this is what you're given. Now, I ask you, given this population, what is the frequency of allele C? What's the frequency of allele C in this population? Now, there's only 2 ways that we calculated allelic frequencies. One of them was counting alleles. Clearly, that's going to be the case. The other one was using genotypic frequencies. You're not given genotypic frequencies, at least not automatically. So the easiest way would be to calculate alleles. So again, on the exam, it's probably going to be less alleles to begin with, and then less numbers to work with. But if you add all these up, right, they're going to come up to be, if my math is right, it's going to be 550. Does anyone know a quick way to do it? If you count the extremes are going to be all 110. 110, 110, 110, let's see. 110, actually, no, I forgot about the 60 because these are odd. Never mind, it's going to be 550 plus 60, which is 610. So, but anyway, let's say you count the alleles, come out to be 610, right? But these 610 are not the alleles, these are what? Right, these are the individuals, well, genotypes. So to calculate the alleles, it's going to be what? It's going to be 610, if my math is correct, times 2. So in fact, let's make it easy. Let's say these are 90. Right? No, I know I have it right. I made 90 just to have this one as 600. Right? So 600 times 2 would be what? Would be 1200. So these are my number of alleles. Now, how many C alleles do I have? What do? This one has none. None. This one has how many? 30. Plus. None. None. 60. Plus. None. 160. 2 times 2. Plus 80. 90. all divided by 1200, and you work it out. So again, don't worry about the quick math. You can easily do it. But the idea is you always look for the C allele. In the homozygote, you times it 2. In the heterozygote, you times it by 1. In the homozygote other, you times it by 0. Okay? Now, this is one question. The other type of questions, and again, I'm going to only concentrate on problems real quick. The other type of question would be if I told you the frequency of big C is 0.25, let's say. The frequency of big C little is 0.5, and the frequency of little is 0.25, which obviously leaves the rest. Now, what is the frequency of big C? Excuse me, I'm done. Now here you're not given numbers. That would be my reasoning. Well, everyone's reasoning. There's no numbers, individuals that is. I'm given frequencies. I've got to use the second method. What does the second method tell you? The second method states that the frequency of one allele is what? Is all the homozygotes plus what? Half of the heterozygotes. So F big C is equal to what? It's equal to 0.25 plus half of 0.5, which is equal to 0.5. So that would be probably part 1 of the equation, or the problem. Part 2 would be, is this in Hardy-Weinberg equilibrium?
Yeah.
And it would be in Hardy-Weinberg equilibrium, because to prove it, what you need to do is take this and go back and see if it matches. So if I have the frequency of big C, what is the frequency of 2 big C's? 0.5 squared. That's 0.25. What's the frequency of big little heterozygous? It's going to be 2 times this times that, which will always be also equal to 0.5. That's in Hardy-Weinberg equilibrium. Now, some may argue, well, aren't they all going to be the same? Why? Because you took this to calculate this, and now you're taking this to calculate that again. Of course they're going to be equal. And the answer is, of course, not. Because you can prove it by almost any switch that you can make in this. Not almost all, but most. Let's say you had a different, you had 4, 3, and, well, let's say 4, 1, and 5. Now, what's the frequency of, no, in fact, we can do it, yeah, we can do it to still keep 0.5. Let's do it to still keep 0.5 here. This is not in Hardy-Weinberg equilibrium. Why? Because the frequency of C is still going to be 0.5, right? Because now all I need to do is take 0.4 and add it to 0.2 divided by 2. I'm going to get 0.5. But notice, if I go back, it's not going to give me the same. 0.5 squared is 0.25. It's not in Hardy-Weinberg equilibrium. Right? And that's another Word file that I posted. So please go through it if you have any question. Now, other type of questions could be something